Maybe. Hello, everyone. Thanks for coming. This is a talk I really enjoy giving, because it talks about the basic building blocks of how UI toolkits work in general. So, just a bit about me. I'm Lucas. I'm Brazilian. I've been in the UK for quite a few years, and I work at Facebook. I joined recently to work on UI frameworks there, and having a lot of fun there. So this talk, the main intent from this talk comes from seeing a lot of hand-wavy UI code out there. So, and I think this mostly comes from not being aware of like how the basic principles of a UI toolkit work. So, in many ways, this talk will be about the basics of Android. So, I expect that like I'll be talking about things that most of you have heard before. But at the same time, but on the other hand, I'm taking a kind of like a twist here. So, I'll be talking about the basics, but instead of going through the basics from an API, a pure API perspective from outside, I'll be talking about the basics of Android, and in a way talking about the basic principles of like what makes a modern UI toolkit from inside out. So I'll be talking about a lot of like how Android implements the basic building blocks of like from the moment you write any UI code to the point where it's actually displayed on screen. And my intent here is not to go like too deep on like how everything works, but just deep enough so that whenever you're writing your next UI code, whenever you're doing a request layout, you can have a very clear picture of what's going on in the system. And I think this helps a lot in terms of like making good decisions and writing robust UI code. So this is about the basics from inside out. So if you look at the just like quick question, like has anyone worked on any toolkit that is like maybe like 15 years old or something like this? Like really old school stuff. Like anyone? Yeah. What? Just an example. Like, okay, Swing. Whoa, okay. So yeah, I've worked on some old stuff too. So I worked on like GTK1, TCL/TK, like really old like Linux stuff. Like I worked on a lot of like UI development for the Linux community for a long time. So a lot of my background comes from it. But if you look at like any toolkit like that you've like worked with in the past, like they all like work with like based on three major like concepts. The notion of layout, which defines of what the size and the position of like things on screen. The notion of like drawing these things on screen, like the more fundamental like drawing calls, and a notion of input events, something that responds to user interaction and updates what's on screen accordingly. So this is the same concept everywhere in any UI toolkit you can see you're seeing out there. But until like fairly recently, the notion of like a UI toolkit has always been focused on the layout part and input, because motion was not a primary concept or a primary aspect of most of the UIs that you've seen like I don't know 10 years ago, for example. So most of the UI toolkits were basically in essence they were basically a bunch of like APIs to nest things together and show stuff on screen. And if they had a notion of motion, it was a very rudimentary notion of motion. So you could animate things through time, but there was no formal concept of time so that like motion could work predictably in such system. So you don't need to look like too far in the past. Like if you look at Android pre-Jelly Bean, like it's pretty much very hand wavy in terms of motion. Like this is like a core piece of the UI framework that I'll be talking about in more detail in a second. But whenever you did like a request layout, there was no notion of like what kind of target display am I running on? When should I do updates on screen? So the way it did was the core component of the UI toolkit was basically a handler that would take request layouts and just run them whenever they can. So you would get all sorts of problems. And like if you think about like pre-Project Butter Android, you had very unpredictable behavior for animations. You would have the right API, but for some time you would have very unpredictable behavior for motion. So what they did with Jelly Bean was basically adding a more robust system that synchronizes everything that happens on screen through a very simple system that I'll be covering in a minute. So whenever we talk about modern UI toolkits take motion as a core concept in their architecture. And this involves having a very clear notion of time, and that notion of time has to be like has to account for the target display that you're running on. So, and this mostly comes from the need for dynamic, very dynamic kind of UIs that we're building nowadays. Like just before this talk, there was a talk about transitions and animations, and that's what people expect nowadays from like a modern app. So the notion of time, and that's like a very like common concept in any modern framework nowadays, is that you sync with the frame rate of your display. And this is where the 60 frames per second comes from. Like most of the devices that we're like targeting for Android these days, they have a frame rate that varies from like 58 to 62 frames per second. And you don't want to do more than that because you would be doing like unnecessary work. You will be doing like drawing calls when the display is not even ready to update yet. So you don't want to go more than your frame rate that you can that the device supports. And also you don't want to do like less because you'll be janky, right? And you also want to do, and more importantly, you want to update only when it makes sense to update, to avoid problems of tearing. In case you've never heard of this term before, tearing has to do with like displaying incomplete state on screen. So you basically show a bit of the previous drawing state mixed with the next one. So the basic idea behind using Vsync, the frame rate of your target display, is that you're always in sync when it makes sense to refresh whatever you're showing on screen. So in Android terms, Jelly Bean introduced the notion of a choreographer. And that is pretty much the same model that any modern UI toolkit follows nowadays. So you have this notion of frames, and the frames are done, like updated in sync with the refresh rate of your target device. And one important aspect is that you only update anything on your view hierarchy when Vsync is triggered. So this means that whenever you're doing request layouts, whenever you're doing invalidations, what essentially you're doing is queuing an operation in the next frame. So whenever you're thinking about anything you're doing in the UI, split time in frames, and whatever you're doing now will be queued in the next frame. And that's a very important concept to frame any questions about like your UI code on Android and in any other toolkit for that matter. So, and the kind of things that you'll be queuing in each frame is you want to resize something, you want to hide or show something, you want to redraw something, or you have an input that updates the state of your UI in some way. So in which case you want to redraw or relay out something. So if you look at like Android code, and I really recommend like having a look at this class, like view root impl, and then this one choreographer.java, because this is basically how everything works in the UI toolkit, and it makes it easier to frame any questions you have in terms of bugs or weird behavior in your UI code. So the choreographer, as I said, it hooks into the Vsync, which will have a callback that will be triggered every 16 milliseconds, roughly, for like the average device that we have nowadays. And then it will call this do frame. And the important thing is when you talk about like Vsyncing your UI toolkit, the first like impression you get is like that the UI would be like doing a lot of work all the time. Every 16 milliseconds it will be doing something. But in practice, the toolkit will only do work when you queued something. So this if like in do frame is basically that. Do I have anything to do? If I don't, I just bail and don't do anything. But if I do have things to do, this is the order where the order of things here matter quite a bit. So, and this again is the classic model for modern UI toolkits nowadays. So first you handle input, your touch events, your key events, and as you would expect, like these things could invalidate or change the layout of your UI. So if you're dragging something around, you will be setting translation or rotation or something, right? If you're pinching something. So you first handle input, then you handle animations, which are essentially callbacks that you're queuing through your object animators and such. And last but not least, you do the layout traversal, which is the main focus of this talk. So you always run things in that order, and so that like you have a predictable pipeline for updating your UI. So a very core component of the UI toolkit is called view root impl. So it's what connects your window manager, which is not something we interact directly with, and usually in your apps, with the view framework. So the way it works is you have a root. The view root impl always sits like at the top of your view hierarchy. So your root view in your activity is not the actual root of your view hierarchy. It's always the view root impl. So this means that whatever invalidation, whatever request layout calls you make, it will always bubble up to the view root impl, and that's what's going to trigger draws, layout, measure calls, and which will like at the end of like a traversal generate a new buffer that will be consumed by the surface flinger, which will use the compositor to show stuff on screen. So this is the connection that your app in the view framework has with the system UI and such. So going a bit specifically on the view framework, like I think it's like everyone is aware of like the basic APIs of like Vue. So the Vue framework works based on 3 steps: measurement, layout, and draw. And what I'll do here is like detail a bit of like how they work and a bit of like how they are implemented in the UI framework. So Transversal is this recursive operation that happens or that may happen at the single frame in the UI framework. It's a recursive operation that travels like depth first in your view tree. And for each visited node or each visited view, it will do something. And the first step for any layout traversal is measurement. So, and the way it works is it will call measure on every visited view in the tree. And then it may or may not call your own measure implementation. So whenever you implement a custom view, on measure is what you implement yourself, right? But there are cases where on measure will not be called. So, I'll give you an example of one optimization that the framework has to avoid excessive on measure calls. So in KitKat, Google introduced the notion of lazy measured. So as you know, there are certain kinds of layouts that trigger multiple measurement calls in a single pass, right? So the canonical example is layout weight in a linear layout, or even like relative layout in general. It usually involves multiple measure calls in its children. So the view framework before KitKat has a very simple caching system that whenever you provide the same measure spec pair to it, and it has already done work with that pair, it won't do anything. So your own measure call will just be will not be called. But for multi-pass layouts, like relative layout, what happens is you provide several pair of measure specs to your view, and basically that completely breaks your simple caching system, because if you're caching only the last measure spec pair used, if you provide another one, you will call on measure again, right? So the idea with lazy measurement is that on the measure call, it has this hash map with all the pairs used in a single layout pass, and whenever you get a match, you don't do anything, and if you don't, then you call on measure. But what happens then is you will guarantee for most of the cases that you only call on measure once when layout is called. So just to summarize, so this will be we'll check in a sparse array, do I have this pair of measure spec? Yes, then I'll just queue a on measure call in the layout call, which is only called once per layout traversal in each view. And then if not, then you do call on measure and cache that. And then if you queue a lazy measure call, so just before your layout call, you'll do the on measure call. So this is basically a solution to avoid multiple on measure calls on multipass layout implementations. And this drastically reduces the number of measurements per traversal. The one thing that is interesting here about this is the view clears this cache when you call request layout on it. And this means that where you call request layout matters, because you'll be clearing cache up to the root. So that's one of the cases where picking which view you want to call request layout on matters in terms of what's going to happen in the next frame. So here's just, this is just something to keep in mind. So the next step after measurement is layout. And the same thing will happen. It will call layout on the view and then on layout on your implementation, right? And what this will essentially do, and this is kind of like a simpler aspect of the traversal, it will just set the frame, which will set left, top, right, and bottom on the view, and it will also call your on size changed callback if you have something implemented there, and if the size changed. So, and layout is only called once per view in a traversal, while measurement can be called several times. And the last step is drawing, and the way the modern Android works, as you probably heard many times so far, since Honeycomb, is the notion of display lists. So what the big change from pre-Honeycomb to the hardware accelerated world was that drawing calls became essentially a recorder of drawing operations that get collected and then executed in the GPU. So the way it works is whenever you do a draw and you need to draw again, and I'll talk about invalidation in a minute, it will essentially start a canvas which will basically record all the commands you call, like your draw rect, draw bitmap, and so forth. And at the end, we'll end this list, and then this will be executed by the graphics pipeline later. And here's the practical tip. So measurement, layout, draw, they always happen in that order. And that means that layout, if you're running layout, it means you've got measured. That's an invariant of the UI toolkit. And if you're running draw, you definitely have your size. You definitely got laid out already. And here are more specific smells to look out for. So if you're using get measured something outside layout, be suspicious, because get measured width and height is basically something that you use in your layout implementation. So if you're using anywhere else, like you're probably dealing with some really fishy implementation of your UI code. So look out for that. If there are cases where this is valid, when you're like manually measuring something for some reason, which you should probably not be doing, but there are cases for that. But look out for that. The other thing is like new allocations. Like allocations during layout traversal should be very deliberate. So it's kind of okay to allocate new things on layout because it only runs once in each traversal, and layout doesn't change that often. So that's probably fine. On measure, it might be called multiple times per traversal. So if you're allocating stuff there, like you might be doing too many allocations, because it's not necessarily called only once. So try to avoid that. And on draw, it will be called on each frame on animations, and drawing state is something that tends to change a lot more often than layout. So pretty much don't do it. Like if you have a new something in your draw calls, like you probably should rethink your code. And the one thing that I find like interesting, I just thought it would be fun to bring this up. Like I've seen a lot of people using post as a way to say, after the layout, I have my size and do stuff, right? So you have something like this. So in your activity, you need the size of my view, and you do a post runnable, and magically you have your size there, and you feel all like, yeah, that's working great. But the thing is, this just happens to work by chance. You're not actually being deliberate with this code, because runnables, posted runnables on the main thread, have no connection with how the UI framework works. You cannot guarantee that will be called before or after the next layout traversal. So just to give you a sense of why this happens to work, is that whenever you're about to run a traversal, what the UI toolkit does is it adds a barrier in the looper. And that's the UI toolkit telling you, I want to own the main thread now. I don't want any runnables that you have like random code to be affecting what I'm doing now. So it adds a barrier, does the traversal, and then it removes the barrier. So this is why this happens to work most of the cases, because it adds a barrier. So your runnable most of the time, or almost invariably for this case in the activity, will be called after the layout traversal ran. But you should not be doing this because you want to be deliberate about your code. So you should be using trio observer. So whenever you mean after layout, use either on pre-draw listener or on global layout listener. That's you being deliberate that, like, I know the layout is done in the next frame, and then I can definitely rely on get with to return the right thing. So don't rely on post to mean next frame, because you don't know when the runnable will be actually executed. And the funny thing about on pre-draw listener is that it's the basis, it's the core API for the transitions framework. I blogged about like how the transition framework works. So if you're curious about the inner workings of like the machinery of that, like have a look at this blog post. But the basic technique, and I think it's cool to demonstrate that because it's a very obvious way of like understanding how to orchestrate layout and animations. So what the transition framework does is it saves the state of all views before the next frame. It waits for the next layout state. It restores the state of the views to the previous state, like by just calling set translation, set rotation back to the original values. And then it creates animators to animate it back. So it's kind of faking an actual layout transition. And that's a deliberate code. So you know it's the next frame. So you know what you're doing. So talking about changes. So I covered like how you display stuff on screen. But what happens when you want to change something on screen? What happens when you do a request layout? So request layout is used like everywhere in any view interaction you have. So if you set visibility request layout, if you set the size of something, a layout param, you request layout. If you enter a new screen, that would be a request layout somewhere. So, and back to the frame idea. Whenever you do a request layout, what you're doing is bubbling up or queuing a traversal in the next frame. So that means, and that's another thing to keep in mind too, is like if you call request layout 10 times within the same frame, there won't be 10 traversals in the next frame. It's only one. So you only do, what you're doing is this, is like traversal run in the same, should run in this next frame. That's it. If you call 10 times, it's basically the same request. So there's not a one-to-one match between request layout and traversals. And the way it's implemented is pretty simple, actually. So it basically checks, do I have a parent? Yes, then call request layout on a parent. And this will bubble up until the view root impl, which will then queue a traversal in the choreographer, which will then run the thing I just described. And just by looking at this code, you can see that like the deeper your view hierarchy is, the more costly your request layout calls will be because it has to travel all the way up, right? So this is one of the many reasons to keep your view hierarchies as flat as possible. Cool. Invalidation. Invalidation in hardware accelerated world kind of like changed a bit in terms of like the nature of the damaged region, but overall it works like similar in the sense of bubbling up, but it behaves a bit differently than request layouts. So the way it does is it marks the view as invalidated, and it's not covered in this code like bit here, but if you have a hardware layer in the parent, this will like destroy the layer and request that layer to be rebuilt. So has anyone ever used the developer tool to like flash green whenever you're invalidating a hardware layer here? Hands up. Yeah. So that's this case when you're invalidating something within a parent that has a hardware layer in it, and you want to avoid that because this is super expensive. So, but what's being shown here is that when you mark as invalidated in the next traversal or in the next frame, in the next draw call, this is not the draw call from the view. The public one is the internal draw implementation. But it will mark this thing as recreate display list, and then that display list code that I've shown in the previous slide will be run again. It will start collecting commands and then get a new display list for the view. And last but not least, animation. So whenever you're using Object Animator, like when you do post on animation or you create any kind of like view animator, what is actually happening is you're posting a callback directly to the choreographer. So your posted animation is essentially doing like the post callback in the choreographer for animation. And just to remind you about the original like core code in the choreographer, it will run in the second step for the callback animation. So this means that your callbacks will be called after handling input and just before the next traversal. And again, this is just something to have in mind because whenever you're wondering about how animations interact with input, for example, handling, you know that the order is guaranteed to be this one. So basic tips. They're actually the stuff that everyone repeats all the time. But I think they actually make a lot more sense if you understand all this machinery I just described. So the first one is actually not obvious, but you should never, ever do a request layout during layout, because this is probably the worst case scenario for traversals. Because what the framework will do is it will do a whole traversal, and at the end it will say, did any view request layout during traversal? If yes, it will do the traversal all over again. So in a single frame, it will do 2 traversals. And in terms of performance, and I think this is basically my main intent here. Like, we keep talking about all these tips, keep your view hierarchy flat, but like if you understand that the way traversals work, this becomes a lot more obvious. Like, that's the kind of work you're doing. You're visiting views all the time. And if you keep your view hierarchy as simple as possible, this means that this traversal will be a lot faster than you would if you had a lot of views. And multipass measurement, like all these canonical examples, probably something to keep in mind too. So if you're doing multipass measurement, if you're doing layout weight, keep an eye on where you're using it. Depth matters a lot. So if you're using multi-measurement like stuff at the top of your view hierarchy, this means you'll be measuring a lot of stuff in each traversal. So avoid especially multipass measurement on higher up in your view hierarchy. And like something I've been advocating for some time, like if you should feel comfortable to write custom layout code whenever you feel like there's a core aspect of a UI that can be done a lot more efficiently because you know what you want, instead of using stock layouts and do the magic incantation in the XML to lay things out the way you want. So I have some code samples in this blog post, and there's a lot of discussion about different techniques to use if you want to flatten not only your view hierarchy, but flatten views completely. So. And just a little note about the probe. Probe is this development tool that I released last year. I'm not doing a good job maintaining it, but it's functional, so you shouldn't have a lot of problems using it. But the idea is that you can intercept view calls, and you can see how your traversals are behaving. So you can basically catch your draw calls, and maybe you want to do things like, I don't know, you want to log every time something gets a request layout in your view hierarchy, and you want to see what is going on. So that's a very useful way of or handy way or easy way to do these kind of things. So I learned a lot of the stuff that I'm talking about in this talk by just running probe in my UIs and seeing how it's actually behaving. How many measurement calls are being done in this view specifically in my UI and so forth. So just if not only for logging the behavior of your traversals, this is super useful. And you basically deploy this in your own create call in your activity, and you're all set. And yeah, I mean, we're Facebook has this thing that we're probably at the extreme of everything you ever thought about Android development. It's super it's a super complex system. So there's some really hard problems to solve on the layout stuff. And there's a lot of people in London working on really deep layout stuff. So if you fancy working on these things, yeah, we're hiring. So just let us know. And that's it. Questions? Thank you.